So next, we have a talk on analog memristive computing by Professor Alex James. Could be an extension of, could be a continuation of our panel discussion on AI analog hardware circuits. So before moving to Professor Alex James, let's have a quick review of his profile. He has completed his PhD from Queensland Micro and Nanotechnology Centre, Griffith University, Australia. He is currently working as professor with Kerala University of Digital Sciences, Innovation and Technology, Kerala. Professor Alex James is also in charge of Maker Village, one of the leading electronics incubator facilities in India. He is the member of IEEE CAS Technical Committee on Nonlinear Circuits and Systems. He was an editor board member of Information Fusion 2010 to 2014 and currently serving associate editor of IEEE Access and IEEE Transactions on Circuits and System 1 from 2018 to present. He is senior member of Institute of Electrical and Electronics Engineers, life member of ACM, senior fellow of Higher Education Academy, fellow of British Computer Society, and fellow of Institution of Engineering and Technology. So over to you, Professor Alex James, for your talk. Thank you.
Okay, thank you, Chitra. Are you able to hear me?
Yes.
Okay. Thank you. And the slide is visible as well, right?
Yes.
Okay, thank you. Okay, so what I will do is to some extent pick up from where we left in the panel discussion to some extent. And to set the scene, why we need like analog or why we should care about analog still, like, and it may be good to start with thinking a little bit about brain. And and there are a lot of systems today which are basically inspired by the human brain, and each day we uncover something new, which we can use to build like algorithms or take up like the current chips and try to improve the performance of it, and benchmark it against like the brain. So few things whenever we think about the brain that comes up very often is like low power, the learning capability that it has, and relatively much smaller size or high density for the related to the task that it can do. And over the years, like when we try to do this mapping or reverse engineering in a sense of mapping functionalities or to look at like the structural aspects of the brain, like how the data transfer happens within the brain or how the features get formed in the brain. There is to some extent like architectures from the computing side which may be compatible, and some architectures which are not that compatible. So traditionally, like if you look at the bottleneck always has been that you have data transmission between like memory and processing, that one could argue that with increase in high speed design, so you know, we can with lower technologies, we can to some extent deal with that. At the same time, you also have like in-memory computing approaches where it most closely resides with the idea of the brain, where you're not really drawing a distinction between like a memory and that of the computation. And very often, you know, one can argue that brain is full of memories, and the synapses that drives many of these intelligence or logic and reasoning that we have in the brain to great extent is part of memory itself. So that has often inspired researchers in our community at large to think of in-memory computing and cognitive architectures as being one of the leading approaches to go ahead to match up with the brain capabilities of learning or that of power or a smaller size. Now, why would we put an effort in this when we can have like very good algorithms uh, which can outperform a lot of the architectures in hardware that we in the last 20 or 30 years have developed? Um, and one of the prominent reasons for that is to look at miniaturization to a level that we can make like devices intelligent, make it autonomous, make it more distributed in nature, rather than having to rely heavily on like one large computing resource, like a cloud-based system. So can we completely remove cloud? May not be possible, but a lot of offloading of those computing can happen close to the sensor if we have very good AI chips. So edge intelligence, the way I would like to group it is based on how close they are to the sensors and how they are to the large infrastructure. So we have like a low energy processing in some devices which are mandatory. When it comes to a lot of sensors, this is the case. You might be running devices with battery power, and because you want to keep it for longer duration, you want to have like really low energy consumption on the AI processing that you would do. Whether it's a co-processor or whether it's integrated to the sensor, you really want to keep your energy benchmarks really low, even when the density of the computation is very high. So that is on itself like quite a bit of challenge, and we can call that as on-device intelligence. And then there are like a class of systems which requires like whatever you do, you would need like a more amount of energy, but at the same time they are devices which would still communicate with the intelligent processors. So for example, like you have a drone, and maybe not all the things you want to collect and process need to be in the drone, but part of it could be something close to the device that you would hold to control those drone. So part of it may be like a local processing just near the base station, which would usually would need like much more energy than something that you could run close to the sensor. And then you have like far device intelligence, which is more to do with, you have data collection far, your processing is done in a device, in a cloud, and then you are sending the decision back to the device, which is one of the most popular approaches. You can see plenty of like mobile applications to devices work on the cloud using the various IoT architectures that are out there. So driving that will be those algorithms and architectures, deep learning architectures and others, which purely pushes the performance, looking at like high inference rate or achieving like training, which would optimize the way to such an extent that you achieve like global or local minimum or a global maximum, what you're looking for a system, in case of whether you're trying to optimize or you want trying to like take it apart into two distinct sets, like in a clustering or that in a classification problem. So why should we consider or bother about analog? A lot of things in nature is analog. Naturally, many things are analog. Even best of the digital signals that we see, they are also read by the sensors as mostly analog. And we always have like some thresholding mechanism to convert that analog information into a distinct digital. Even the way we see digital in natural systems, it's based on threshold, which would vary from one organism to another. So the cells behave like that from one human to another. there is a lot of variation. So the thresholds that you would set will be different compared to the threshold that is set in another cell in another organism. So in that sense, like most of the information that we have in nature, they tend to be analog, and we need to have some operation, some thresholding operation or some encoding operation to convert that into meaningful digital encoding. So sensors, the things that capture things in analog, and computations, even if you look at the mathematics, the way you do the computation, they are mostly analog. Even the discrete form of computations are also analog. Any kind of addition, multiplication, divisions, all the operations that we do are naturally analog. Now, many of these operations, very often we need to translate that into digital to make it realizable in chip, which is definitely like a matured field, and you can very easily build such systems. But at the same time, like there is a merit to look back into, can we do something natural? If there are circuits which could do the computations in analog and yet not be power hungry, and yet be miniaturized, and if we find a way to transmit the signals without losing power, then we have a case for it. So if we are to process signals near to the sensor, the question of errors in the transmission is greatly reduced. And at the same time, you can take the advantage of various like analog circuits that are out there, or the knowledge in the analog circuit can be put in building certain systems. And that's what the community has been trying to do in the last several years. So why then look at like memory computing? I mean, you can always go for CMOS-based analog systems or any other systems. And there are plenty of like computational systems that you can build with various passive and active components. So why would we worry about Memristor? So one inspiration, like very often, is again going back to the brain, like seeing the brain as like memories and connection of memories. And you have like a lot of highly dense connection or dense cells. So the density is important. For some reason or the other, if you look at like the density of neuronal cells across like various organisms, human brain would have like one of the highest densities of neurons per cubic centimeter. So this definitely tells you that density is important if you want to achieve like higher order of like intelligence of some form, which machines can't achieve. So density is important. The second part will be to actually really see the intelligence as memory to a great extent. Whenever we are talking about in-memory computation, we are just limiting ourselves to a great extent. Okay, we do vector multiplication and we find a way to speed up that MAC operation. But maybe perhaps this goes beyond that. If you see that memory when you are actually having like a architecture to encode your information into those memories, it's no longer just acting as a way to just store that information. It's also the information itself and how it is represented. So those memories or encoding in those memories are probably defining the features that get formed as analogous to a brain. So in a sense, like intelligence to a great extent is how we process or how we store things in the memory, and how we read things in the memory, how we write things onto the memory. So another important aspect that one would need to think about is the energy benchmark as well. Like density, whenever you try to push the density higher, then you are looking at like ways to optimize the energy as well. Many a times what happens is when you place various uh, components close to each other, you have all sort of interferences or non-idealities and other things that come into play. So all these things coupled together, what it does is it puts a lot of overhead on the designer to come up with like circuits or systems which would compensate that. And it ends up largely complicating your design considerations or algorithmic considerations or architectural related considerations. So always like density versus energy is a very tricky thing. And this is something that unfortunately we'll have to live with as we scale down the technologies further, or when you have to deal with like newer devices all the time. So memristors, of course, like offer like a high density, at least in theory, this is the case. And in practice, there are some issues with scaling like the number of memristors within an architecture in a reliable way. But as such, if you look at discrete devices and if you want to create like a large set of discrete devices at high density, this is perfectly fine. This is perfectly doable. So there may be a lot of applications where this can benefit, but at the same time, there may be a lot of other applications where architectural consideration will be equally important when it comes to achieving high density. And the hope of all that is the memristors could eventually be able to help in emulating the brain at a very low energy. Now, if some of you are not familiar with Memristor, this diagram pretty much like gives a high level picture of like what Memristors would be. It's a class of devices that we are talking about. So it's not really it's not really one particular device that we are looking at, and the community as such hasn't really agreed on what is the standard memristor. So what is the best memristor or the benchmark memristor that we could use? So that's always a open. There's still like an open problem, both from the device side as well as like from a circuit designer's point of view, as of to select which memristors to use. And many times we either work with what is best available for for us to use and implement, or that would meet certain requirements of like specific applications in terms of like the voltage levels that is required, or the threshold voltage to switch the devices, or to number of levels that you want to have, like conductance, number of bits you want to write in your architecture, and so on and so forth. Now, as such, like a signature of a memristor is the pinched hysteresis loop, where you can see you have like a low and a high resistance in your IV characteristics, and they are very much dependent on the kind of pulses that you use to program those, and the kind of frequencies that you operate with. That will change your resistance, or in a way, whether you call it resistance or conductance. Many times, like conductance may be a better word to use to program the devices, yeah, simply because you're you have parallel devices being used, so you can simply add the conductance. So it's easier to represent it in terms of conductance in arrays, as opposed to like having it as resistors. So there is this flux term and a charge term. So the flux term, what we are talking about here, this is linkage flux, and the charge which you would see across the two-terminal memristor device. So the device as such, if you look at, there are like a lot of challenges. One of the biggest challenges is device-to-device variability that one would encounter with memristors. When you try to fabricate these devices, even best of the matured like memristor technologies that we have, they all have like a large device to device. Maybe small arrays, you don't see a lot of variability, but then when you try to repeat it, you try to repeat the fabrication even within the same wafer, you would have large variations that you would observe. So that is still an issue in some applications, but there are like there are many other applications where variability could be of use, especially taking into account that variability in your design, whether you know designing a neural network or maybe in cryptography and other things. There are many devices to select from PCM to ReRAM to STT-RAM and so on and so forth, which basically show the resistive behavior, and that shows this hysteresis behavior, where you can control the conductance of the device. You can, in an analog ways or discrete way, discrete stable states rather. Because one thing is to program it to a particular value, another thing is to keep those memristors at that particular value that you programmed it to. So you have to see like whether those conductance that you're programming it to are actually stable, and if you and what's the kind of like precision or that you want to achieve with that. So there are various models based on physics, based on experimental data-driven models, behavioral-driven models that you would observe today. Each one has got its own advantages and advantages. One thing when it comes to selecting the model that becomes more or less important is like, is it the right kind of model for the device that you have used? So you basically you probably need to look at the switching voltages. You need to look at the variability, how much variability aspect can be taken into account in your model. Can you introduce or like add noise to these models, like various forms of noise to these models? Is it fast? In simulation, sometimes what you would observe is because of the kind of like model equations that are used, maybe there are some differential equations or there's some other equations which may not work well in a particular like set of conditions. So in those cases, like you need to have like that model selected such that, you know, for that particular application, the range, the constraints of that models are very clear when you are using it. So selection of that model, something close to what is realistic memristor is always like a still like an open problem to a great extent, because not all memristors, like physical memristor, behave the same. So fitting that into like a memristor model is also something that needs to be carefully done. Another aspect that you would see is like aging and reliability. Most of the memristors do age. There are concerns of reliability, from stuck-at fault errors to something like a reduction in the maximum and the minimal resistance or conductances that the memristors would be able to achieve and to be able to be programmed. In addition to this, there are some practical issues also that comes up when you try to connect like an interface circuit to the memristors. You can also see certain things like read instabilities that will change your currents or introduce like current errors, output current errors, which also needs to be considered in your design. You can also see some of the memristors also have like PCMs would have conductance drift. Need not be always a bad thing to have such effects. You can always use that to your advantage in designing systems which would benefit from that. Conductance changes are very common to have, and there are a lot of reasons why you would have those. Noise related issues from thermal noise and few other noises which are not still very much fully considered in the models. For example, there are many noises that would come. And last, you would see interface electronics and the programming logic. That's also equally important. Many a times you would have to come up with like dedicated like circuits just for doing that, or peripheral circuits which would do that. Not just during the training stages, it may be also required occasionally to fine tune those circuits, because you're imagine like when your um, device conductance get drifted or like changes or their variabilities, you want to some extent fix that, or keep push it back to those values which are close to your idealistic values that you might initially planned it for. So you are looking at interface electronics and programming logic to be figured out in your designs. So typically crossbars are one of the very popular ways in which you can arrange these memristors for making it a meaningful, making it meaningful for neuromorphic computing or like neural network implementations. But they also have like certain issues that you would see. All the device related issues that you see with memristors, they also affect like your crossbar. Typically in a crossbar, what you would want to see is like you would have rows where you are feeding in like your inputs, and then you are reading out the currents through the columns. And in this case, imagine a simple crossbar like this, a 2x2 crossbar, where you have like voltage V1 as one of the input, and then you are reading the current I1. So you have like say two possible inputs to go in, one for the memristor with conductance G11 and another with conductance G21. So basically what you are doing there is weighted summation of inputs. So your weight in this case is conductance. Uh, but then if you look at the crossbar without any other control, you can see the current would sneak path to the other columns which were not selected or which were not intended to be used. So there could be a leakage current that passes through the other columns as well. So that is generally like the generally known as the sneak path currents. And that of course is going to like add to the error of like I1 there, because there is some current flowing through your device, maybe to I2. And conductance variability on top of that is going to make that error in the readout current I1 even more. Or if you have like device aging or signal noise or read instabilities, all those things could add further to that error. So your dot product multiplication or weighted summation of inputs that can have like errors because of all these different issues. So one simple way to deal with that is you add a switch to select the devices which you want to on, and you only you switch on those devices or switch on those columns, maybe go one at a time, maybe the simplest possible way. So adding like a switch close to the memristor helps with that selection and to reduce your sneak path currents, one possibility. But then you also have that issue of like whenever you put a transistor, the transistor can have leakage current, so that also could come into play there. And each of those currents that you read out of that columns, in a way, you can say that this is basically reflective of a simple neuron model, where that part represents your a column would represent a neuron. Of course, you would need like on top of this an activation function connected to your readout part of your columns. And another thing is like conductance are usually positive values, and if you want to have negative weights, then you would need to apply some tricks to come up with negative values. Either the input, some of the input need to be going negative, or you can take two columns and one conductance to be greater than the other, and that way you can take a differential or a difference between the conductance to generate like a negative weight. There could be a couple of ways in which a few or more than a couple of ways in which you can achieve like negative and positive weights with the same crossbar. So what we introduced, like, I'll just introduce like one of the things that we recently did was to take a normal crossbar and then convert that into like a bit more what we like to call it as super resolution. And it's a very simple approach. You just like connect the two columns, two rows, and give it the same voltage. Now, when you do this, the approach looks very simple, but at the same time, it does a lot of interesting stuff. Um, Before going to that, you need to find a way to program these devices. So you can program it, these nodes, like by selecting those individual memristors with those switch transistors that you have. And you can apply like certain set of pulses in a sequence way till you achieve the conductance that you are targeting. So if you look at the figure down below, the graph which shows the conductance. So based on the sequence of pulses that you apply, you can move around the conductance. You can increase or decrease the conductance using the set or reset cycles till it reaches the target values that you want it to have. So basically, you need these set of like peripheral circuits which would switch the voltage levels of the pulses, the amplitude of the pulses, and things like this. Those control needs to be there to make that happen. So whenever we are looking to set the conductance value, we'll go through some of these like programming cycles till it reaches those values. And we repeat it for all the Memristor devices in the network. The simplest possible thing is you program one device at a time, or you can also do many devices at the same time by selecting the columns or rows at once and applying like similar. If every device needs to have very, very different values, then again, like, you need to come up with like, various strategies how to go about selecting those. Do you do it like one at a time? Do you do multiple things at a time? There has to be some strategy that needs to be developed around it. So analog conductance, like in theory, like all the memristors, you can program it to any conductance level that you want. Even the binary ones, if you look at even the binary levels would have drifts. So whenever you have like a drift, I mean, even that drift can be used for making like analog conductance. So theoretically speaking, like almost like any memristor device you take, there would be certain level of like conductance range that you can program the device to. And now in practice, the thing is like when you're trying to build like analog system, many times, like imagine you have a weight value and you map that weight value to a conductance value. Now this mapping may be a linear mapping, it may be a non-linear mapping. So whatever mapping that you do, say it's a one-to-one mapping, and this you have a target value that you want to program it to, and you put like all the effort of going through all the cycles, programming the set and reset and reach those values in. But now the problem is like very often when you are reusing the system, like say inference operations and other, these conductance value tend to change. And some of the values may be very hard to keep there because of the device physics, that particular like device characteristics, how they are made, or the properties of the device would be limiting it to be programmed to infinite number of like conductance levels. In fact, it's always like limited to like a few set of levels which are very stable for that particular operation or particular application. So in the sense, like number of conductance level that you would confidently program with a memristor tend to be limited to few number of levels, and which we will call as like node resolution of the crossbar. And the idea of super resolution is by combining these memristors in parallel, like, somehow can we like increase the nodes. So suppose like, you're trying to connect these two G11 and G21 in parallel, you could see that the effective conductance, you can just simply add those, and you see there are two memristors, each one having like two levels, a high level and a low level. And when you combine them, what you see is three unique conductance level that you can achieve. So you're basically like translating a two-level system to like a three-level system by doing that. But clearly, this is not a very, it's not a quite advantageous thing to do. So if you take like a m number of like bi-level conductance memristor, what you would typically see is the unique conductance will be of this order. It will be 2, then 3, 4, and so on and so forth. So if you start with one memristor, it would have like 2 levels. If you take 2 memristors, you would have 3. If you take 3 memristors, you would have 4 levels, and so on and so forth. So not much of an advantage. But then this also represents something called one simplical number pattern. It shows like one simplical number pattern in a way. So we would like look at it a bit more further in terms of increasing the number of levels as well for the memristor. So if the memristor has got only one level, stuck at like only one level, then you have like only one conductance value that you can have as unique conductance. And if you increase the number, you can see like the unique conductance here is 3, because all you have is like three levels for the single memristor. But as and when you increase the number of memristors per node, you can see the unique conductance start to increase. And as you increase the memristors further, you can see it increases further. Now, if you put that together to a large number of levels, like many memristors, you can increase the number of levels to very stable, like 8 levels for sure in a lot of the memristors. And just by adding more number of memristors per node, you could see the unique conductance actually increases quite a bit. And if you have just 12 level, 8 12 level memristors, you are looking at like a unique conductance which is like very high, so which gives you quite a large precision to work with for the weights. And in fact, like this interestingly shows like a simplical number pattern. So I was trying to visualize it as a geometry and stuff like this, and it's basically a polytype. There is an interesting theory in mathematics of polytype numbers, and it actually falls under one category, and it was a very interesting thing to see. So what we could do is like we could then build like, for example, a CNN with such node. So you have the crossbar nodes representing one of the convolution layers. Do a simple mean pooling by taking an average average circuit. An RELU block can be put in. Simple current converters and all those things, and build like a CNN out CNN with nodes which are like super resolution nodes. So if you see here, these are bi-level. The nodes has like only 2 levels, and that gives you for a CFAR 10 like 82% accuracy. And for the same 2 level with 8 node memristors, you get like a push the accuracy from 82 to 90%. So the precision actually increased just by adding the number of memristor nodes. And you can see as you increase the number of levels further, very easily you can achieve like a larger number of unique conductance levels, which is increasing the precision of the weights, and which in turn is like increasing the overall accuracy. And it's actually able to match up with the ideal like accuracy, which was like I mean the number of epochs, everything constraints, everything is kept same for those comparison. So you can see like for the same scenario, like just by increasing the parallel nodes, you are able to do this. And another interesting thing very often that happens is R on and R off ratio when it changes. Like usually systems have a very large impact on it. When you program, depending on like whether you program for the conductance particular value, you start with certain R on and R off. And if your R on and R off values are different for the same memristors, you would see that the performance or the errors in your crossbar also becomes different. So as you increase the number of conductance levels, here the relative current error that one would see, it actually decreases by quite a bit. So from 17 percentage, it reduces to 8 percentage for one memristor. Whereas like if you look for a 6 memristor node, these values are much lower. Like you can see even for a 2 level conductance node, you are looking at 2.5 percentage as opposed to something like 16 percentage. So there is a dramatic drop in the errors that you would see. Um, Similar to that, like aging, one type of aging, I mean, there are many different types of aging one can consider. One difficult type of aging that we looked at is like when the R off is decreasing and R on is increasing. When this happens, again, we noted that we observe very similar trend in terms of increasing the conductance value, the number of levels in the memristor and increasing the number of memristors, you could really lower the current errors that you can. So in a way, just by doing this, you know, one would be able to improve the precision quite a bit. And another thing is like when you do this, obviously the area is going to increase for the crossbar. And you could still leave with that simply because many architectures wouldn't need like the in every part of your circuit, it may not need the same kind of precision. So there may be some neurons which would need like more precision, some others would need less precision. So just by controlling that, you can reduce the number of or the usage of the crossbar and reduce the or optimize the area. Especially if you are thinking about inference, you can go about optimizing the area based on the precision required in each of those inputs, and thereby like control your area at the same time achieve like high precision in computation. So some of the questions that one would ask in robustness: can variability of a memristor be compensated to manufacturing process? This is still like a very much open question. Device people and process people are working on that. It still remains as an open problem. Can architectures compensate variability of memristors and signal noise? To a great extent, yes. You could see like some of the architectures are better at like compensating those variabilities, some of them are not. So how you come up with like architectures is going to have an impact on that. Learning and tuning of weights also can help you compensate for various performance losses, and this can be part of the design that you would consider. And how to select an architecture, this is an open problem. So there was some discussion about automating AI chip. Like we had like tried to do this, like many other people, I guess. So what we looked at is specifically like memory-based system, and we applied like a multi-objective optimization search to figure out the impact of. I mean, usually when you try to optimize the architecture or when you're looking at neural search algorithms, they purely focus on the number of neurons or like number of the hyperparameters, optimizing hyperparameters based on the accuracy one need to achieve. So what we did was we looked into the hyperparameters, and also we looked at like various other aspects such as the power and the aging related things, the variability and everything taken into account in trying to identify what blocks are most optimal to be used in an architecture. So for example, try it like something like CNN with genetic search. I mean, you can see various hyperparameters that are selected here, ReLU, TANH, sigmoid, which one would give you better, the first thing is to figure out, like, is it ReLU or using TANH or sigmoid, which they are going to give you better accuracy. Likewise, learning algorithms, which would give you a better performance. Figure out that, take that as part of your, um, optimization, or figuring out what are the circuit blocks. So the result of that is, like, you have various circuit blocks. Now you put those things together and see which of those networks are most of. There are three networks which gave like very almost same accuracies, but at the same time you can see their areas are very different. So network 2 and network 3 has same area, but 2 gave like lower power consumption. So whereas like network 3 gives smallest processing time. So the most efficient design is something that you select based on all these parameters, not just looking at the accuracy or inference accuracy. So inference accuracy in all of these cases was same, but then we automatically need to go and select like which blocks would give you like the best hardware performance as well. So in that sense, like using a genetic search and the multi-objective optimization for that like help to do that. Training neural networks, it's still like under variability is always a challenge. The more variability and sparseness that you have in the network, it becomes harder to train. And very often the reason for that is like when you do more, make it more sparse and other things, you leave open the generalization part more. And generalization very often like works against the optimization of that local minima that you want to achieve. The global optimum that you are trying to achieve may not be always the best way to solve that problem. There are many problems where you would like find the local minima, but then as and when you have a new set of inputs coming in which are not in the trained data, completely different, but it's in the same category, it may not recognize it because it's very much tuned to work for that set of training examples that you are given. So global optimum may not be. Another thing related to this training is like this generalization. We saw this like very interestingly to see when we compare like HTM and CNN LSTM. HTM is very much like a architecture focused on generalization. It's very much inspired by brain networks and other things. And if you try to implement that with Memristor, crossbars and things like this, you can see like you need like a lot of arrays to work with. And there you have to randomly assign like weights and so on and so forth, which was quite useful for training the HTM. Whereas the problem was that like all the generalization is very high, it's difficult to train, and accuracies were low compared to a CNN and LSTM, which were relatively easier to train and had higher performance, but the generalization is not as good as like that of HTM. So this is something like one needs to consider when it comes to like applications. So maybe something like for robotic application, HTM might have an use, whereas for classification and things like this, CNN and LSTM would be a better choice. Another training challenge that you would see is generative networks. So if you build like a GAN, you would see the difficulty of that to train. Like the training would be the hardest part. The inference would be the relatively like the easiest part to deal with. And you can compensate for noise and other things in generative networks as well. Like we had like GAN, I think you can search like analog GAN. And this was basically purely like analog based circuit. And then there is a Pixel CNN, which is recently, very recently, like published in I think IEEE Nano, but it's even more difficult to train. So the although like even algorithms wise, it takes a longer time to train, and if you try to implement in hardware, it takes even still longer time to train. I'll try to conclude soon. So another thing, recent thing that we looked into is like to how to utilize like the parallelism of the quantum in dealing with some of the training issues of SNN. So what we did is like not just look at, I mean, there are many ways to train like SNN. And one of the successful ways always has been like, you pre-train it using like back propagation or something, and then translate those into like encodings in the SNN. And that tend to give you very good accuracy. But even those accuracies were typically like not as good as like that you would see with CNN and others. So what we did was we took part of the training to the quantum and made like a feed forward kind of training. Um, and interestingly, what we could see is that SNN could beat some of the CNN or like traditional SNN. This quantum as SNN could beat that. So the idea here was like, okay, our traditional SNN will remain the same, whereas the quantum part, like you can train it in a quantum computer. So you can have multiple spiking neural networks trained in the quantum at the same time. The spiking neural network itself will run in your edge device. So that was an interesting thing. At the same time, like when we tried to translate like CNN to quantum, it didn't give that higher accuracy. Probably because like the number of epochs may not have been sufficient there. And it also means that SNN was training faster than CNN QC, um, so which was also like an interesting result to see. So parallelism, I think, can help, and this may be a possible direction to think about. And to conclude, I would just put a thought of where we are in this. So currently, we'll call it like AI 1.0 of AI chips. And what we are largely looking at is neuromorphic 1.0 and neuromorphic 2.0, where we are trying to improve the accuracies of or the architectures, efficiency of the chips for very specific problems. And we are uncovering many applications that goes towards generalization of the AI chips, such as SNN is like always have been trying to do that, and always have been like the reason, one of the reason why CNN or like deep learning architectures always was seen superior was because of performance accuracy. But at the same time, when you try to see various other applications where you need like faster response times and other things with like low energy benchmarks, SNN was better. And although the accuracy is less, so lesser accuracy doesn't mean that it's a bad thing. It's just that it may not be the right kind of application that we are looking at. So going further to this, at some point in time, we'll have to think about generalization much more seriously, simply because many systems would want to learn by itself. Like if you want to make the systems achieve like the brain benchmark, without generalization, it may be very hard to achieve. Even if you put together a lot of like very smart AI chips, which is focused at one particular task and it does really well in the task, but when you try to combine it, it wouldn't generalize. simply because any change in even a small change in experience would like make that specific application or specific chip not work as efficiently as like it was programmed it to do. Whereas in a generalized going toward general intelligence, you would want the chip to learn and understand new experiences better. So that will be one of the big transition points that we are looking at. And once we achieve that, probably the next level of thinking would be collective AGI, where you would want to put several of these chips together to build larger systems which could compete with like human intelligence or even cross that. And there are a lot of other efforts where the super intelligence or general intelligence is being like looked at from a human computer interaction point of view, where the community people are trying to utilize the power of the brain along with the computational power of the chips. So probably human machine intelligence probably is going to be the barrier that we are looking at in terms of super intelligence. And clearly that's all these things are very much debatable, and clearly all these things are something like the community would have to work from all the different angles, from algorithms, from architectures, from devices, from circuits, from top to down. Okay. And I end with that. These are the talk was largely based on the super resolution crossbar. This is a recent paper with Professor Chua, that I did recently, and it will appear in the 50th birthday of Memristor. And the AGI related some of the things you can read from this paper, and few of the other works which were based on that. Okay. I think that concludes my talk.
There are 4 questions on the chat board.
Okay.
One of the ones, I'll take the ones which you can answer very quickly. The ones which are longer, maybe we can answer them later. This is from Sivasundari. What type of simulation tool can be used for AI Memristor training?
Simulation for Memristor training. So what we did was, there were some of the architectures, the way we were looking at, they were purely inference related tasks. So whenever it was purely inference related tasks, we used libraries, taking the models from the okay, there were in some architectures, what we did was we used an experimental model. So the data points were extracted from the experiments. We took the average of that and then used that. And then at an architecture level simulation, for calculating accuracies and other things, we were using Python basically to simulate that. And some of the other systems like circuit level simulation, all of them were done in SPICE. Those simulations basically taking into account specific technologies. And the Memristors, even in those cases as well, we were looking at the devices that we had and what would best match with those. So we tried several models. It was not just one model. For example, once we had GNOME devices and we were using a GNOME model. And in some other cases, we were using modified BioLec model and then fitting that. And there was, in some cases, we were using Verilog with extrapolated data and so on and so forth. So it was very much dependent on the problem that we are looking at that we use these models.
Yes, there are 3 other questions, but I think we should move on and we can answer them by chat messages later. Or would you like to take them now?
I can type that back in so that the time is not waste.
Okay. Because or else it will be too late in India by the time we start.
Okay.
Thank you, Alex. Our